Gyronix.
Welcome back. In this lesson, we will discuss another circuit analysis method and my favorite, the node analysis method. Shortly, you will know why this is my favorite, and let's get started. And this will be our topic outline. We'll discuss what do we mean by node voltage, and of course, the node analysis method itself. So first is the node voltage. Node voltage is simply the difference, okay, between 2 points, or what we call a node, okay, in an electrical circuit. So for example, we have this simple circuit, and we are asked to determine the voltage across this resistor, let's say V1. So the voltage across that element is simply the difference, okay, between the nodes. This one right here is the node which has 5 volts with respect to ground, right? And this one is also a node which is connected to your 9 volts, which means if you are going to measure the voltage across this node, you have 9 volts. So the voltage across this element is simply the difference between your 9 volts and 5. Okay, so the difference between its terminal, right? So 9 minus 5 is 4 volts. So that's how basic the node voltage concept is. So let's have an example. So the node analysis method is simply used to solve a non-node voltage, and we have here a familiar circuit. This is the one we use in the KCL/KVL. So I don't need to explain how to set this up. Okay, we have steps. So if you're not familiar on how to set up the circuit, you can review the lesson for KCL and KVL. Okay, but right here we have a circuit set up ready for calculation, and the node analysis method simply uses the KCL concept, okay, to formulate the equations. Okay, so we have here the KCL at A. So we know how to write the equation for this one. So the current going in is I1, which is negative, of course. Currents going out are I2 and I3, which is the summation are equivalent to 0. Okay, so what's next with this? We represent current in terms of voltage and resistance. So I1 is simply what? Okay, of course, V1 over R1, I2 is V2 over R2, I3 is, of course, V3 over R3. So the next step is we will use the concept of the node voltage. And V1, which is the voltage across R1, is equivalent to the voltages between its node or terminal. So the first terminal of R1 is this one, which is connected to what? Okay, VO, and the other terminal is connected to VA. So which means the difference between the terminal is what? VO minus VA. Okay, so that is the voltage across R1. How about V2? Okay, V2 is the voltage across R2. So again, the voltage across V2 is equivalent to the voltages between its node, this one, and another one. So what is this node? VA. This one is what? This is ground, which means that is 0 volts. So which means your V2 is equivalent to, okay, voltage at that node A minus 0. So again, the node voltage is just the difference between the voltages of the nodes or terminals. Okay? So V3 is simply the difference between the voltages on its node or terminal. Okay? This terminal of V3 is connected to VA, and this one is connected to ground, which is 0. So which means your V3 is also VA minus 0. Okay, so that's the basic concept of the node analysis method. And one thing to notice here is we have only one unknown variable, VA. Okay, and take note, VO is always given, that is the voltage at the source. So using only the node analysis method, the node concept, so we are able to determine the value of the unknown voltage. Okay, instead of having that 3 equations, 3 unknown. So to understand it more clearly, let's have an example. We have here a quite familiar circuit. Actually, this is the same circuit we use in KCL and KVL. So we are expecting the same result. But this is some sort of review. So let's review the steps to set up the circuit. So first is to select the ground node. Then with respect to that ground, we label the voltages. We have VO, V1, V2, and V3. And the next step is what? Of course, the current flow. Current is going into the positive terminals, right? And of course, IO is from negative to positive. So we have I1, I2, and I3. And this time, since we are using the node analysis method, we don't have to create a voltage loop. Okay, since the node analysis method uses KCL implicitly. So let's analyze the KCL at this node. Let's say node A, let's call it node A. So we know how to formulate the equation for this one, KCL. So we have current going in, which is I1, negative I1, plus I2 plus I3 equals 0. And the next step is to represent in terms of voltage and resistance using Ohm's law. So I1 is V1 over R1, I2 is V2 over R2, and I3 is V3 over R3. So the summation is equivalent to 0. Next is we will apply the concept of node voltage. So first is V1. So V1 is equivalent to what? Okay, the difference of voltages between each terminal or node. This one is connected to VO, and this one is connected to node A. Okay, so of course your V1 is VO minus VA. Of course your V2 is what? Okay, we have VA minus 0. Okay, VA. So this one. Okay, your 0, this one. So the two terminals. So that is the voltage across V2. How about V3? Okay, of course, V3 is, this is the terminal which is connected to VA, right, or node A. So this one is connected to ground, which is 0. Okay, so the summation is equivalent to 0. And let's separate this term. We have common denominator R1. So we have negative VO over R1. And of course, negative times negative is what? Okay, positive. So we have VA over R1. So let's clean up that 0. Okay, VA minus 0 is equivalent to VA over R2 plus VA over R3 equals 0. And we only have, okay, common variables. So we can factor that out. So the next equation would become VA times 1 over R1 plus 1 over R2 plus 1 over R3. So I think this is quite familiar to you. Okay, we send that format in our KCL and KBL exercise. Okay, next is to substitute the values. And first is we'll transfer this negative side to the right side. Okay, so that is equivalent to, okay, V over R1 positive. Then substitute the value of R1, which is 100 ohms. Okay, so this 100 ohms. R2, okay, that is 1000. So 1K, 1000. R3, 330. Okay, this one. So that's equivalent to, of course, VO is 5 volts. Okay, so over R1, which is 100. So let's calculate the left side of the equation. So that will give us 0.01403 VA. It's equivalent to 5 over 100. Okay, so what's next? VA is, of course, we can cross multiply. So this one to 100. Okay, so it's going down to the denominator. So we have 5 over 100 times 0.1403. And that will give me VA is 3.56 volts. And this is the advantage of using the node analysis method. So that's why this is my favorite. So if you recall, when solving the circuit using KCL and KVL, we need to formulate that three equations, three unknown, right? But using the node analysis method, we simply determine real quick, okay, the unknown node voltage. So we have now VA is 3.56 volts. And now using this voltage at that node A, which is 3.56 volts, we can calculate all the voltages in the resistors using the node voltage concept. So first is V2. So what is V2? So the difference of voltages between this terminal, which is what? Of course, your V2 is VA minus 0, which is equivalent to 3.56 volts. Okay, next is what? Okay, V3 is in parallel. Of course, they have the same voltage. And V1, this one, right? So the terminal which is connected to VO. And another terminal is VA. So V1 is VO minus VA. So 5 minus 3.56. And V1 is 1.44 volts. Okay, so this is the voltages across the resistors R1, R2, and R3. Next is the current. Simply, that is direct substitution with the formula. We have now our voltages. So we'll be using Ohm's law, V1 over R1. Okay, I1 of course is 1.44 volts divided by 100. Okay, 14.4 milliampere. I2 is V2, which is 3.56 divided by 1K or 1000. So I2 is 3.56 milliampere. And the last one is I3. Okay, V3 is also 3.56 divided by R3, which is 330. And I3 is 10.79 milliampere. And the next one is the power. Of course, we'll be using V1 times I1. So we have now our current and voltages. So for P1, simply multiply 1.44 by 14.4 milliampere, and that will give us 20.74 milliwatt. So for P2, so simply we have 3.56 volts multiplied by 3.56 milliampere, and that will give us 12.64 milliwatt. And the last one is P3, okay, which is V3 times the current I3. So that will give us 38.41 milliwatt. Okay, so let's have another exercise. Okay, we will be using the node analysis method for the circuit. So the same requirement, will calculate the current, voltage, and power. Okay. So what's the first step? First step is to select the reference node, the ground. Label the voltages with respect to that node. So let's say we have VO, V1, V2, V4, V5. I make V3 last because if you notice, this terminal is connected to the positive of V2 and negative of V1. So you choose if this is positive or negative. The answer is either way. Right? As long as you follow the convention in our KCL. But I will choose this terminal as positive. My reason is this one is 330 ohms. So there is less resistance at this terminal going to the ground compared to this one, which is 1K. But again, either way, you can choose this as positive, this one is negative. As long as you follow again the KCL convention. So there's no problem with that. So let's say this is how we set up the polarity of voltages. The next step is to label the current going onto the positive terminals. Okay, so we have, of course, IO is the currents flowing through the source from negative to positive. But for the resistors, we have going in I1 to the positive terminal of R1, I2, I4, I5, and I3. Next is to label the node. Let's say this is our E1, this one is E2. Okay, so let's analyze first this node E1. So we'll formulate the equation for KCL at that E1. Current going in is what? Current going in is I1. Okay, so this is negative. Of course, going out are I2 and I3, so which are both positive. Then we'll express in terms of voltages and resistance. So I1 is V1 over R1, I2 is V2 over R2, and I3 is V3 over R3. So the summation is equivalent to 0. Okay, next is the node voltage concept. So V1, okay, so the difference between the terminals. So V1 is what? Okay, VO minus E1, right, over R1. So that is the current I1. Next is V2. Okay, this one. So the difference between terminal, which is E1, and the ground, which is 0. Okay, E1 minus 0. Next is V3. So where's V3? This one. So the difference between terminal, this is E1 and E2. So your V3 is E1 minus E2. So the summation of these terms is equivalent to 0. Okay, next is to separate this term. So they have a common denominator R1. We have negative V over R1. So negative and negative. Okay, so we have plus E1 over R1. So remove that 0. Plus E1 over R2 plus E1 over R3. So we separate this one. Minus E2 over R3 equals to 0. The next step is to factor out these common terms. Okay, so we have negative VO, okay, E1 times 1 over R1 plus 1 over R2 plus 1 over R3 minus E2 over R3 equals to 0. Okay, next, let's substitute the values. First, let's transfer this negative V over R1 to the right side. So it will become positive. Okay, so we have that unknown variable, E1. So minus E2 over R3 equals to positive V over R1. Next is the values of resistances. Okay, R1 is 100 ohms. Okay, so R2 is this one, 1K. 1000. R3 is another 1K. Okay. So minus E2 over R3 which is 1K. So equals to, okay, VO is 9 volts, R1 is 100. And let's calculate this first. Okay, so this will give us 0.012 E1. So E2 over 1K is 0.001 E2 and equivalent to 9 over 100 is 0.09. And this is our equation 1. And the next equation we will derive using the node at E2. Okay, so another KCL. So current going in are I4 and I3. So they are both negative. I5 is positive, right? So that is the KCL at E2. Okay, so the same method we will express in terms of voltage and resistance. So I3 is negative V3 over R3. I4 is V4 over R4, and I5 is V5 over R5, so the summation is equivalent to 0. So next, let's apply the node voltage concept, V3. Okay, this one. So that is the difference between E1 and E2. So we have negative E1 minus E2 over R3. Next one is V4. Okay, so what is this node? This is connected to your VO, and of course this one is E2. So V4 is VO minus E2 over R4 plus V5. Okay, V5 is simply E2 and the ground, right? So the difference between E2 minus 0 over R5, so the summation is 0. Next is to, okay, separate this term. So common is R3, negative E1 over R3. Okay, negative and negative. So positive E2 over R3. So another, okay, separate this term. So we have negative VO over R4. Okay, the same, we have negative, negative. Okay, so E2 over R4, positive. So plus E2 over R5 equals 0. Okay, next is, let's rearrange. So these are the common variables. So let's have the voltage source first. Okay, the negative V over R4. And let's factor out E2. Okay, so these are the denominator, R3, R4, and R5. Okay, so common is E2. E1 over R3 equals to 0. And next, let's substitute the values of resistances. And of course, the same process. So let's move this to the right side. And to have the same format with our equation 1, so let's have E1 first, okay, negative E1 over R3. So this one. Then the E2. And of course, positive VO over R4. So let's substitute now the values. Okay, R3 is 1K. R4 is 560. R5 is 330. But the first one, okay, R3 is 1K, right? Okay, so we have 1 over 1K plus 1 over 560 plus 1 over 330. So this is equivalent to 9 over 560. Okay, R4 is 560. Okay, so let's calculate now the values first. Okay, for E1 over 1000, that is negative 0.001. Next is this term here, and that will give us 0.005816 E2. So 9 over 560 is 0.01607. And this will be our equation 2. Okay, so we have now two equations. But I think it's a little bit hard to comprehend, right? 0, 0 something. What I can do here is to scale the equations. What I mean by scale is I can multiply this by 1000 every term. Okay, so 0.012 times 1000. Okay, that will give me 12. So 0.001 times 1000 will give me 1. So that's why remaining is E2. 0.009 times 1000 will give me 90. Okay? And the same with equation 2. I will scale that up, multiplying by 1000. So this must be the same factor. Okay, so we have 1000 times 0.01. Okay, that is 1. And 0.005816 times 1000 will give me 5.816. And this one, the 0.01607 times 1000 will give me 16.07. So I think this scaled equation is easier to comprehend compared to that lot of zeros after the decimal point. So let's use this scaled equation. So we have two equations, equation 1 and 2. So the next step is to calculate, of course, the value of A1 and A2. We can use substitution. If you notice, you can transfer this to the right side. Then, what left in the left side is E1. So you can substitute that value. Then you can calculate. Okay, but of course, I will not going to do that. I will use the matrix form, which is, I think it's much, again, easier and cleaner to work with. So let's represent this in terms of matrix. Okay, we'll use the Gaussian elimination method. So let's collect the real numbers of coefficient, okay, for E1 and E2. So for equation 1, E1 is 12 and E2 is negative 1. Of course, the right hand side is 90. So for equation 2, E1 is negative 1, E2 is 5.816, and the right hand side is 16.07. So this is our augmented matrix. So the next step is, of course, I want in my first equation, I want E1 to lead. And in the second equation, I want E2 to lead, which means my second equation, I will set this E1 into 0. Okay, the negative 1. Okay, I will set it to 0. So this is in echelon form, right? Okay, so let's process this augmented matrix. So how I can make this 0? This negative 1. Okay, I will simply multiply this by 12. So this 12 will be added to positive 12. That will make my E1 0. Okay, so that will be my formula. So all the elements of row 2, I will multiply to 12, then add to row 1. So negative 1 times 12, okay, this one. So negative 1 times 12 plus 12, that is 40. So the same, 5.816 times 12 plus negative 1. That will give me 68.792. So 16.07 times 12 plus R1, which is 90. And that will give me 282.84. Okay, so this is now 0. Then I will again convert this matrix into equation form. So this is now my new equation. Of course, your equation 1 doesn't change. Equation 2, so we only have E2, 68.792. So we don't have E1 since we zero that out. And equivalent to 82.84. So I can simply divide both sides by 68.792. So this one cancels out. And this will give me E2 equals 4.11 volts. So I got now my unknown voltage, E2. Okay, the next step is to substitute that 4.11 to my equation 1. Okay, so 4.11, then of course I can transfer this negative to the right side. So it will become positive. And that is equivalent to 94.11. So divide by 12. Of course, cancelled out. So my E1 is 7.84 volts. So I got now my two unknown voltages. And I can now calculate for the remaining voltages across resistors. So I have now my E1, okay, which is 7.84 volts. And I have my E2, which is 4.11 volts. So using the node voltage concept, I can calculate for V1, okay. So V1 is the difference between the node, okay, that is VO minus E1. So 9 minus 7.84, and that will give me 1.16 volts. That is V1. So next is the current, of course, Ohm's law, V1 over R1. So 1.16 divided by R1, which is 100 ohms, and that will give me 11.6 milliampere. So for power, of course, that is voltage times current. So V1 times I1. V1 is 1.16 and the current is 11.6 milliampere. So the power dissipated by resistor 1 is 13.46 milliwatt. So for V2, so the difference between the voltages on its node, so we have E1 minus 0, or simply E1. Okay, V2 is 7.84 volts. So our current is Ohm's law, V2 over R2. So 7.84 divided by 1K, and that will give us 7.84 milliampere. Okay, P2 is V2 times I2. Okay, V2 is 7.84, current is 7.84 milli. Okay, that will give us 61.47 milliwatt. Okay, so the same process. So this time V3. Okay, the difference between the node, which is E1 and E2. Okay, V3 is 7.84 minus 4.11, and that will give us 3.73 volts. So for the current I3, simply Ohm's law. So V3 is 3.73 and R3 is 1K. So that will give us 3.73 milliampere. So for power 3, of course, V3 times I3, V3 is 3.73. Okay, current is 3.73 milliampere, and that will give us 13.91 milliwatt. Okay, so V4, the same concept. Okay, V4, so the node or terminals, this is connected to, okay, VO, and this one is E2. Okay, V4 is VO minus E2, which is 9 minus 4.11, so V4 is 4.89 volts. And current, okay, another Ohm's law, so V4 over R4, so 4.89 divided by 560, and that will give us 8.73 milliampere. So for power 4, of course, the same formula. So voltage is 4.89 times 8.73 milliampere, and that will give us 42.69 milliwatt. Okay, and the last one is V5. So V5 is E2 minus 0, okay, ground. Or simply E2. So we have 4.11, okay, using Ohm's law. So voltage is 4.11 divided by the resistance, which is 330. That will give us 12.45 milliampere. And of course, for V5, so the same formula, voltage is 4.11 times the current, which is 12.45 milliampere. And that will give us 51.17 milliwatt. Okay, so this is the end for this circuit analysis method. So this is the node analysis method. And I hope you learn a lot from this lesson. And now I think you can now compare the difference between using KCL and KVL in solving circuit parameters and using the node analysis method. Okay, so you understand now why node analysis method is my favorite. Okay, so it is much easier to use. Right? Again, I hope you learned something a lot from this lesson, and see you on the next one.